over the past 5 to 10 years, there's been a lot of innovation on really, orders of magnitude reduction in the size of the satellites, of the affordability of the satellites.
What advancements do you each see as being most critical for advancing microwave sounding technology in the next, 5 years, let's say?
The spatial and temporal resolution of the geo data, and we blend it with the more accurate precipitation information provided by the sounders at slightly lower resolution.
We can continue to replenish those satellites every 2 to 3 years and add all the improvements that these guys are coming up with new technology for sounders to put up on a very timely and inexpensive basis.
We're excited to share a really good conversation with you here today. I have 3 fantastic guests, and we're going to be talking about how we're advancing weather prediction through microwave sounding technology specifically. So to kick things off, I first introduce myself. I'm Kelly Peters. I'm VP of Marketing here at Tomorrow.io. If you guys wouldn't mind just going down the line, introducing yourselves and telling us about your title and maybe a snippet about what you do.
Yeah, hi, I'm Joe Munchak, and I am the Principal Atmospheric Data Scientist at Tomorrow.io and also the Instrument Scientist for our Microwave Sounder program.
All right, hi everybody. I'm Jen Splaingard, and I'm pretty new to Tomorrow.io. I've been here almost 3 months. I lead the Space and Sensors team, so the team that is putting together all the hardware and integration and launch for the constellations of sounders and radars.
Good morning. I'm Bill Blackwell. I am a laboratory fellow at MIT Lincoln Laboratory, and I'm the principal investigator of the NASA Tropics mission.
Fantastic. Well, we're so excited to have you guys. We'll pass it back. Perfect. To kick things off, a question for the group. So we've been at AMS now, 2 days, whether it be something you gained here or, just looking forward generally. What advancements do you each see as being most critical for advancing microwave sounding technology in the next, 5 years, let's say? And Joe, we can start with you.
Sure. So the first thing, and it's what we're doing at Tomorrow.io, is increasing the revisit rate. And that's made possible by the miniaturization down to CubeSats, which makes us able to do high quality measurements a lot more frequently because they're a lot cheaper than the traditional ways of doing it from large satellites. And so that's something that we're going to see by the end of the year, and that's going to impact nowcasting products. It's going to make weather forecasts better, both with traditional methods and with AI. Now, one of the farther, I think, trends that we're going to see with the next generation is going to better spatial resolutions, and that's something we're further enhance the precipitation. It's really good for tropical cyclone. And I think it's something that's going to be unlocked by some of the advances in AI that we're seeing at this meeting, because AI can just handle the much larger volumes of data that you're going to get with high resolution measurements that currently would get discarded by traditional data assimilation methods. So I think that there's a lot of short-term and longer-term advancements that we're going to be seeing that I'm really excited about.
All right. Jim?
Awesome. Thanks, Joe. I think the thing I would add that I think is awesome, and one of the reasons why I even came to Tomorrow.io is the problem that we're solving globally. And as Joe mentioned, miniaturization, and as technology's gone forward, we not only have the ability to get the high revisit rate, but with that constellation that we're launching, we get full global coverage, which just does not exist today, especially at that revisit rate. So that's really exciting. And as space has become more accessible with SpaceX and ride shares, the other thing that's really exciting is that we can continue to replenish those satellites every 2 to 3 years and add all the improvements that these guys are coming up with new technology for sounders to put up on a very timely and inexpensive basis.
Yeah, I'm excited about all-weather data assimilation. So the millimeter wave bands that we're flying on Tropics and Tomorrow was flying on their sounders are very sensitive to precipitation and clouds, and the models are getting much better about handling that information. And I think there are going to be a lot more advances in the future to, fully improve the forecast and utilize the data from, ice particles and water vapor that we are getting better at, but aren't quite perfect yet. So I think that'll improve quite a bit.
Makes sense. And sticking with you, Bill, what would you say is, perhaps one of the most significant challenges in optimizing the microwave sounder design for things like, temperature and moisture, and maybe how are some of these advancements, perhaps as you just spoke about, able to address those things?
Right. So the conventional things that we always try to optimize are the resolution, like Joe was mentioning. So, the temporal resolution we're addressing by launching more satellites. And then there's radiometric resolution, the noise in the measurements we try to improve. And we're actually getting to the point there where the noise is not limited by the receiver, just being limited by the thermal background, what we're trying to measure. So the receivers are getting very good. So I think the most headroom for improvement are things like spatial resolution, spectral resolution. We can fly digital spectrometers now to get very good spectral resolution. We're able to fly larger sensors now, even on relatively small platforms for better spatial resolution. And I guess the unconventional side of that answer has to do with things like how we operate the sensors. We can consider things like data-driven observations, targeting, configurability of the sensors to try to react to things in the scene and optimize the sensor to make a better measurement of those attributes of the scene.
Got it. Thanks for that. And speaking of sensors, Jen, question for you then. So shifting a little bit, how would you say that the developments on board in terms of processing and the downlink capabilities are maybe changing our approach to the data latency and quality control, for example?
Well, so we're certainly learning a lot about that right now. We have 6 satellites on orbit and launching them at different inclinations and learning how the ground stations the partners with ground stations that we work with around the world really interact with those. So I think in the future, as we advance more ground station capability and plan the inclinations that we're launching these satellites, we'll have a better and a more rapid ability to get higher latency and meet the requirements for not only high revisit rate, but getting the data down in a really timely and now manner.
Makes sense. And related to that, Joe, can you think of, perhaps any specific examples where we're able to combine the sounding data with any other observational source in a way that has really improved the retrievals or the profiling, accuracy?
Yeah, so one of the things that we do operationally at tomorrow.io is called unified precipitation, and that is a blend of geostationary-based precipitation, but it's augmented by our sounders because the geostationary, it's very high spatial resolution. It comes in every 10 minutes, but it's not directly sensitive to precipitation because you're only seeing the cloud top. So we do use AI to blend it with the sounder data so that we try to get the best of both worlds. We get the spatial and temporal resolution of the geo data, and we blend it with the more accurate precipitation information provided by the sounders at slightly lower resolution. And so we find that you can get better by combining them significantly than either one alone. And that skill not only lasts when we have a satellite overpass, but up to an hour afterwards.
Awesome. Does anyone have questions? I know it's a small group here, but anyone, have a question for the group from the audience or otherwise? No pressure.
Question for Bill, actually.
Here.
So my question, Bill, microwave sounders have been around for a while, right? I mean, it's not a new technology. Can you explain a little bit what it looked like not that long ago versus what it's doing now and what you think the capabilities in the future as we continue to, innovate around this not new technology, but technology we can advance? So can you talk about that?
Right. So you're absolutely right. Sounders have been flying in space since the early 1970s, right? The MSU launched in 1979, I think, right? So the evolution have been largely, incremental advances in things like the antenna size and the number of channels that we've flown. But the core technology innovations really haven't happened very rapidly over the course of that development. Over the past 5 to 10 years, there's been a lot of innovation on really, orders of magnitude reduction in the size of the satellites, of the affordability of the satellites. The commercial infrastructure to support these kinds of small satellite systems has exploded in the last 5 to 10 years. So we're riding all these waves. The communication sector has pushed forward things like RF technologies. So the confluence of all these things have really enabled the small satellite innovations that you're seeing now, right? And pushing forward the technologies that we're using for radiometers, making them more sensitive, flying more of them, lowering the cost, improving the coverage. All those things are happening kind of simultaneously.
Makes sense. Thanks. Question for you guys, actually, kind of on the fly here. I promise it's not a hard one. But just this morning, I've been talking to a lot of kids from universities, people just starting to get into the field who are really, really excited and passionate about this stuff. What would you say to someone who's maybe just starting to get into, the new space paradigm, as we call it, and is really excited about sounding technology, for example? What advice would you have for them of just, breaking into this space? Joe, I can start with you if you're willing.
Yeah, so my number one piece of advice is honestly look at the data, and whether it's our data, whether it's Tropics data, nothing I think substitutes for looking at as much data as you can and seeing what you think you can observe, and then I think that the one skill that people have of coming out of college these days, much more so than when I did, is more familiarity with the AI tools and techniques that can take those ideas and transform them into actual products very quickly and easily. And I think we're just going to see an explosion of applications of data sets, not just ours, but all Earth observation data sets, based on what's now possible with these techniques and just ideas that people have and applications that probably weren't even thought of when the instruments were designed.
Good.
I'll just add something from the space perspective. And as someone with a perspective that is relatively new to the weather industry, coming out of school and being at a conference like this, I mean, my advice would be to get out and talk to as many people and learn as much as possible, of course. But as you start your career, and no matter what it is that you start to work on or develop, whether it's space related or not, have a bent for what types of things, given technology and advancement and accessibility to space, can you put up in space without having to go through the full rad hardening, all the environmental requirements, to just experiment with and see what the art of the possible is, and coming up with ideas like that. We are in a stage now where there's just the ability to do more and more, especially at LEO, without a 20-year development program is at our fingertips.
Phil, any final thoughts from you? Yeah.
So just on that point, I think it was mentioned, there's a really tight coupling now between what you might call the data science and the atmospheric science, right? So there's, we're in the world of apps, and there's all kinds of, I think, potential for, a new analysis, new software tools, new programming tools to really take that to the next level. And people can, come in and get a really rich problem to tackle on the data side, on the science side, on the engineering side. It's all kind of woven together in a nice way.
Yeah, fantastic. Well, thank you guys so much for joining us. Any other questions from the audience? Please, yeah.
So better spatial resolution came up a couple times earlier. Do you all see the path for that as going to higher frequencies or larger antenna, or is it the digital signal processing? Like, there's different ways you could achieve that, and I was wondering what you thought would be the most effective way of doing that.
So we're going to take that one first.
Yeah, so I think that we have to look at all of those. I think that there's a lot of complementary information, but I think at some point you are limited by the antenna size, whether real or synthetic. And so, getting to techniques to expand that antenna size that you can get from a smaller platform, and we're pretty small right now. It wouldn't take much, just a slightly bigger satellite to get our footprints down on some of the higher frequency channels. But you have to make sure that you're also sampling the scene right, so you've got to spin the satellite faster. There's a lot of, and that comes with increased noise. There's a lot of trades there. I don't think any of these trades are insurmountable, and I think that for the applications that demand higher resolution, they can usually tolerate a little bit more noise. So I think that we've got a lot of options and a lot of tools we can use. It really just comes at the cost of size, is what it comes down to in most cases.
Yeah, I would agree with all that. I think one kind of new tool that is emerging is our ability to build large format arrays in the microwave for both passive sounding and for radar. And those technologies, again, we're kind of drafting off the communications sector. If you look at something like Starlink with a very sophisticated phased array that it uses as it flies over, we can do the same thing in principle for Earth observation, right? So those kinds of techniques, in addition to a bigger aperture, a more sophisticated electronically scanning type apertures are coming online too.
All right. Great question. Anyone else? One question. Please. No problem. Please. I'll pass you mine.
Thank you. I'm interested in the one comment you made around augmenting data. Do you guys use actual data from weather stations that are already available in the U.S.?
Yeah, so it depends on the product. So your traditional data assimilation ingests everything, including station data and satellite data. The product I was talking about was unified precipitation. So that is a blend of satellite data and ground radar data, to give us the best picture. So where we have ground radar data, we heavily leverage that. But in the 90% of the world that doesn't have ground radar, we're relying on satellites, and that's both our own and the ones that are publicly available, so that we make sure that at the end of the day we're getting the best answer and the best product out to our customers.
Thank you.
Perfect. Well, thank you guys so much for joining us. This was fantastic. We will, of course, have the recording also to distribute broadly. But yeah, Phil, Jen, Joe, really appreciate it. And thank you guys. Feel free to stick around for any questions.